Howdy! Our capstone project is the ADRS. On our team, we have Mark Johnson, Delanka Weersinga, Jason Gilman, and Max Griffith. To understand our problem, we need to inspect two elements of land and air vehicles. Autonomous land vehicles lack the ability to gather large amounts of data in order to gain the situational awareness to move proactively. They are, however, able to carry large payloads with relative ease. On the other hand, air vehicles make up for their lack of carry capacity with exceptional mobility, awareness, and vision. Our system works to combine the benefits of both of these in order to reduce the cost of a survey system while maintaining the full capabilities of both vehicles. Our sponsor set us out with these main tasks in mind. The drone will survey an area with full autonomy. The system will then send a completely blind Land Rover to navigate the area. When comparing our system with current military and professional solutions, we see a missing link that can be filled. In most mapping and survey drones, especially in agriculture and infrastructure, they lack many applications that our system provides. Our system is completely mobile, requiring no connection to the internet and no server to manage the data. This is mostly due to how we've designed our system to gather and interpret the data. We use an image processing algorithm with depth map sensing in order to create a map of the area. Typical solutions make use of light detection and ranging. While this is extremely effective in producing a 3D map, it requires a huge amount of computing. This also limits the ascending altitude of the air vehicle to around 10 meters, with the most expensive LiDAR systems being able to map accurately around 50 meters. With our system, we are able to accurately map an area regardless of altitude and without the restrictions of increased airtime. This means we can map extremely large areas and are mostly limited by our maximum flight time of 31 minutes and the range of our telemetry. To engage our vision for the ADRS system, we chose to develop following these constraints. Low cost, with a camera supporting computer vision applications. Microcontrollers were chosen that would lend themselves well to wireless network connectivity. And we wanted to keep the system safe for all operational use. This problem is separated into 4 different sections. The first is to gather information, next to computer vision, then a pathfinding step, and back to the land vehicle, all being controlled from the user interface. This, subsequently, is also how we separated out the tasks. Now we're going to show you how our system operates.
The operation of our system is controlled through a desktop application that runs on the user's computer. This allows us to consolidate all I/O and user interaction into a single platform. The first thing that the user must do is select the area of operation. To do this, they can use a tool included in the UI. Per our system's functional requirements, the area must be no greater than 1 square kilometer. Once the user has chosen their area, then navigation instructions are generated and then uploaded to the aerial drone. Finally, the drone is launched through the UI. The last 2 steps require the user's computer to connect to the drone's network over Wi-Fi to initiate communication, which again is all handled for the user in the background. At this point, the drone is executing its flight script, which begins with various systems level checks and eventually takes off and executes on the previously uploaded navigation instructions.
After the drone is launched from the UI, it will then perform several self-checks in order to confirm it can maintain stable flight. The drone will then take off to its target altitude and begin moving to its first waypoint location. Here we can observe 3 different scenarios where the drone is launched from the UI in order to gather its data at different waypoint locations. When observing the movement of the drone, we can notice that the drone only moves in a forward orientation. This is because the obstacle avoidance sensors are located in both the front and the back of the drone. The user interface passes several special parameters to the drone. This includes the target altitude and the orientation in which the drone will be taking its recordings. Here we can see one of the left and right eye images captured by the drone. the drone will take 5 images on the left side, move a little bit to the right, and then take 5 images for the right side. This is what allows the computer vision steps to first remove moving obstacles, then stabilize the video, and then finally create a depth map of the overall area. Once the drone has finished gathering all the data it needs at each of its waypoints, it will then return back to its launch location or to a new location determined by the user. Finally, we see the landing being completed by the aerial drone.
After the flight is finished, the user can confirm the landing and prepare to download all of the collected data. Once again, the aerial drone is connected to, and all of the pictures that were taken are downloaded to this application. Now, the software analysis phase is initiated within the UI. This will be explained by Mark.
At the beginning of the software analysis stage, the user is given the opportunity to set depth inferencing parameters. These parameters greatly affect the ability of the system to detect obstacles. Once the user has first selected their parameters, they will be able to see a preview before continuing. The first time the user initiates analysis, the flight data will be loaded and prepared for later processing. During this time, the system is using all of the images for each eye to filter out any motion. This step is to avoid having the Land Rover avoid moving obstacles that won't be present when it finally runs. It takes some time to align all of the images and remove all of the moving obstacles from the input, but this step only needs to be performed once. Once finished, a disparity map is constructed of the first quadrant to serve as a sample for the user. The user can observe the resulting output to confirm that the results are acceptable. If the results are unacceptable, the parameters can be readjusted accordingly, and their effects can be observed by pressing Rerun Analysis. Now that the flight data is already prepared, subsequent sample outputs are far quicker to produce. Once the results are good enough, the user can press Generate Path to perform the full analysis.
This is the generated path that the drone will take. As you can see, it avoids the obstacles which are in white and doesn't overshoot the goal when it traverses its first path east.
After the path has been generated, the navigation instructions are uploaded to the Land Rover. This functionality is very similar to the aerial drone. Also, like the aerial drone, the Land Rover is launched through the UI.
We will now traverse the path that was shown in red on step 6 and is also on the right of your screen. Since the Land Rover is blind, it needs a specified direction. The direction that was specified is south. So as a result of this, the rover will turn left in order to move in the proper direction, that being east. The path generated is based off an orthogonal algorithm, so the drone will not use any diagonals. This is to avoid any potential corner clippings with the drone.
At this point, our system has completed its operation. While it's not crucial to the system, the user is able to stop the timer for data collection purposes.
As you can see, the ADRS system has several advantages over other mapping systems and performs well in all areas of operation. We hope we've proved the ADRS is a cost-effective and efficient solution to all sorts of surveillance scenarios. Thank you for listening to our presentation.